Hi everyone, this is Mrs. Harms. I'm just going to talk a little bit today about gravity, normal force, how they're related, and what roles they play. So we've talked a little bit about gravity before, and in fact, just in our conversation about Newton's laws, we talked about it again. Gravity is a force that attracts any two objects with mass. And I think this is also a really good time for us to talk about the fact that in science, we often use models. And models are a way of understanding things. And that sounds vague, and it is a little bit, but it's intentionally vague. We might have a mathematical model, maybe an equation that helps us understand the relationship between two things. We might have a visual model, um, and there's lots of different models. But models are not the reality of the thing. Let me use an example. Later this year, we're going to talk about light. And you may already have learned a little bit about light. Maybe you know that sometimes we think about light as a ray, sometimes we think about light as a wave, sometimes we think about light as a particle. And the reality is that it is none and all of these things at the same time. And that is because a model is a way of understanding things for a specific application. And so we as humans have sort of given names and pictures and equations to things that help us understand them and help us use them as we need to. Um, but one of the things that can happen in science education is sometimes students feel like they got lied to when they get taught a simpler model and then find out that a more complex model exists. And gravity is a situation where we're going to definitely, throughout this year even, start with a relatively simple model, and then build our way up. And I want you to know that, like, the model we use for the before January portion of the year, um, is every bit as valid as the model we'll use later. It just depends on the situation you're using it in. And so the model that we're going to use starting today is called Newtonian gravitation. It is very straightforward. Essentially, we've already used it when we talked about free fall motion in a previous unit. Essentially, things want to fall down to Earth. So if I have my apple, it will want to fall down towards Earth. It's a very straightforward way of thinking about things, but it really works as long as you're close to Earth. And actually, we can make it a little bit more complex. It really works as long as you're close to a planet or planet-like object. If you're on the moon, it works. If you're on Mars, it works. So it works for most of the places that humans find themselves. However, humans are not the only the things that we're concerned about. We want to think about other issues. And so sometime in January or February, we'll need to talk about what's called universal gravitation. And this is the gravity that we see between two planets, for instance, or a planet and an asteroid, or a planet and its moon. And as that kind of suggests, it means that this really only becomes an issue when we're dealing with, say, a planet going around the sun, and we want to talk about gravity and, as a result, like the orbit of the planet. It'll be really useful for that. But we don't need every single problem to use universal gravitation. Sometimes the easier way is just fine. And if we get time in May, we'll talk about things like space-time and relativity and what that all has to do with gravity, because it turns out we can make gravity even more complex. And there are still a lot of questions we have about how gravity works, and looking at like a universal model for gravity. And so um, keep in mind, what we talk about today is absolutely the simplest version of gravity, but it's a version of gravity that works really well for the cases that we need it to. And so let's think back to last unit when we learned about objects that fall. And we realized that all objects that fall at pretty much the same rate of acceleration. You may remember we did a lab where there was a bowling ball against a house and we figured out what that rate of acceleration was. And so we learned that when an object is in free fall, aka gravity is the only force acting on it, that what we end up seeing is that it accelerates towards the Earth at a pace of negative 9.8 meters per second squared. And this is actually what we're going to use to build our our equation for the force of gravity. Because we already know that in a problem like this, the net force equals mass times acceleration. So if the only force we have is the force of gravity, then we can find that force of gravity from just taking the mass and multiplying it by the acceleration. And I'm going to write mg here. So this is our big equation for gravity. And the nice thing about this is that, yes, on Earth, g equals negative 9.8 meters per second squared. But if we know the g on Mars or the g on the moon, we could essentially do that bowling ball lab on Mars or on the moon. Then we can find the force of gravity close to those surfaces as well. And it turns out that we actually have measured those and we do know what those are. All right, so this is like kind of the most straightforward way for us to calculate the force of gravity on an object. And as we talk about gravity, I want us to talk about another force that goes hand in hand with gravity, and we call it normal force. And I want to outline here, normal does not mean like typical or usual or whatever your normal definition of normal is. It means perpendicular, and that is from math. So we are not talking about a typical force or a usual force. We're talking about a force that is perpendicular to something, and we will see what that is here shortly. I'll also note that you often see this called a support force. And to understand what the normal force is, let's go ahead and look at our friend the apple sitting on a table. And we know that because an apple is an object with mass, it will have a force of gravity acting on it, pulling it downward. But we also know that it can't be in free fall. Gravity can't be the only force acting on it. Why? Because it's not falling, right? It's just sitting there. And that's where our friend, the normal force, comes in. I will usually write this as F sub n. Sometimes you'll see it written as F perpendicular. So the normal force here is actually from the chemical bonds in the table. And those bonds don't want to be broken, which is what would need to happen for the apple to be able to fall through the table. So instead, what happens is that the table pushes up on the apple, and as a result, it supports the apple, which is why this is sometimes called the support force, rather than letting it fall. And that force of those chemical bonds pushing up is called the normal force. Normal, by the way, because it is always perpendicular to the surface. Not this year, but if you're in AP Physics at any point, we'll look at things like a box on a ramp. And in this case, the normal force is still perpendicular to the surface. Now, the place that people can get into a little trouble here is in understanding how big the normal force is. If the normal force and gravity are the only two forces that your apple has, then they will be equal to each other. And I will say, every year I have students who really, really, really want me to put that equation on a test, but I won't. And the reason is that is a little oversimplified because a lot of times the normal force and gravity will not be the only two forces acting on an object. So let's look at a couple examples here. Now, the way I like to think about these problems is by understanding that the job of the normal force is to essentially cancel out all the other forces. Gravity is usually the biggest one, but it isn't always the only one. So let's say I have a box sitting on a table and it has a force of gravity of 100 newtons. But let's say maybe I walk up and I also push down on that with maybe 20 additional newtons of force. And I want to know, what is the normal force? Well, in this case, the job of the normal force is not just canceling out gravity, it also has to cancel out this extra force. So it would end up needing to be 120 newtons. We could write this in an equation. We know that the net force equals mass times acceleration. So if we want the box to just sit on the table, then the net force needs to add up to 0. So what would that mean? It would mean net force minus 100 minus 20 is 0. Net force is 120 newtons. So either intuitively understanding the job of the normal force and canceling out everything else, or going mathematically straight to the equation are both really good ways to handle this. What about the opposite? What if I go and also lift up a little bit on the box? Okay, well here, essentially what's happening is that I'm getting a little bit of help canceling out the force of gravity, right? I get 20 newtons worth of that gravity canceled out by something else. So if I'm looking at my normal force here, I could think, oh, I only have 80 newtons left. Or if we want to go to our second law, the net force is mass times acceleration, which is going to be 0 if the box just stands still. And so we have normal force plus 20 minus 100 equals 0. And you end up with a normal force of 80 newtons. So there is never going to be on your equation sheet an equation for what the normal force is equal to. You're always going to need to use Newton's second law to figure out exactly how much force does it have left to cancel out. All right. Thanks so much. See you later.